Okay, so here's another example of the goodness of fit test using the chi-squared distribution. So number 9 here, an ABC News poll asked adults whether they felt genetically modified food was safe to eat. So, anybody think of an example of a genetically modified food? Fruit? Yeah. Seedless grapes. Do you think grapes normally come without seeds? No. Seedless watermelon. You know, there's a lot, in the United States especially, we eat a lot of genetically modified foods. I'm sure there's a lot more than that. But 35% felt that genetically modified food was safe. 52% felt it was not safe. 13% had no opinion. A random sample of 120 adults was asked the same question at a local county fair. Now that, to me, that kind of raises a red flag that you're asking about food about genetically modified food at a place where there might be a lot of people that involved with agriculture at a county fair, because we show cattle and we show. But anyway, that's where they asked. So they asked at the county fair. 40 people felt that genetically modified food was safe. 60 felt that it was not safe. 20 had no opinion. So those three numbers are observed values. We actually went out and asked people, and we observed those people telling us, 60 of them, that it's not safe, 40 that it is safe, and 20 said they had no opinion. At the 0.01 level, that's your alpha value. That's your chance, that's your probability of type 1 error. We're going to have a 1% chance that we're going to reject our null even though it's true. So at the 0.01 level of significance, is there sufficient evidence to conclude that the proportions differ from those reported in the survey? So basically they're claiming that the proportions in the survey, these proportions up here, these percents, are not accurate. That's what the claim is. So we're going to set up a table and then do a traditional method of hypothesis testing. Can you flip the lights on for me again, please? Thank you. All right, so here's my table. We have 3 categories: safe, not safe, no opinion. We went out and talked to 120 people at the county fair. 40 think it's safe, genetically modified food is safe. 60 feel it's not safe. 20 have no opinion. Expected values. Now, if it said that the results should be equally distributed over the 3 categories, we would just take 120 divided by 3, and we'd put 40 in all 3 spots. But that's not what it says on this problem. It says that a certain percent feel it's not safe. What percent did it say in the problem? It said 52% think it's not safe. So what we have to do to get this expected value, we expect that 52% of the 120 people should have said not safe, or safe. So you take 0.52.
Safe is 35.
And make sure we read it right.
Not safe too, not safe.
35% said it was safe. Okay, let's back off here a second. 35% say safe. So take 35% of the 120 people. So take 0.35 times 120 people. That will be our expected value in the safe column.
42.
42, thank you. We expected to get 42, but we actually got 40. 52% feel it's not safe. So you take 52% of 120 to get the expected value in the not safe column. So take 0.52 times 120 to get this expected value.
32.
You're
Oh wait, wrong number.
62.5?
4.
4? Okay. And then the last percent is, what percent did they give you here? 13%. So you take 13% of 120, which comes out to what?
15.6.
15.6 people are expected to have no opinion. Now, obviously you can't have 15.6 people. So there's no way that our observed values would ever match up exactly with our expected values because we have decimals here. But the question is, are these values in the observed row close enough to the expected values that we can say that these differences are just due to sampling error, that these percents are correct? Or are these numbers far enough apart that we're going to be able to say our percents are not correct? That's the question. We're going to use statistics to make that decision. Here's the null. The opinions on whether genetically modified food, let's change that a little bit. The opinions on genetically modified food are as follows. 35% feel it's safe. 52% feel it's not safe. 18% have no opinion. The null then is that the opinions on genetically modified food
Isn't it 13%?
13, yes. Sorry about that. You're right, 13%. Otherwise it doesn't add up to 100%. The opinions on genetically modified food are not as stated above. That's what they're claiming. They're claiming these percents are wrong. So any questions so far? Okay, we're doing the traditional method of hypothesis testing. The second step is to find the critical values. So you get your chi-squared table out. You look at your chi-squared chart. Your degrees of freedom is the number of categories minus 1. We have 3 categories. So our degrees of freedom are going to be 3 minus 1, which is 2. So you look at 2 down the side of your chart under degrees of freedom. At the top, you go to your alpha value of 0.01. And that's how you're going to find your critical value. So I'm seeing 9.210. You guys agree with that? 9.210. So what we're saying is that here's our chi-square distribution. That our critical region, or our rejection region, is the tail area to the right of 9.210. These tests are always right-tailed tests. So if I get a test value that's above 9.210, then I'll know to reject these percents. All right, next step. To get the test value, here's your formula you use. You take your observed values minus your expected values, you square that difference, you divide by the expected value, then you add them all together. So we're going to do, for example, 40 minus 42 in the numerator, squared divided by 42. Plus, then we're going to do 60 minus 62.4. So someone can do this on your calculator as we go here. Squared divided by 62.4. Then we can do 20 minus 15.6 squared divided by 15.6. That's going to give us our test value. Anyone have any idea what that comes out to?
I got 1.43.
1.43?
I got that too. It's my fault.
Okay. 1.43. So 1.43, notice, falls between 0 and 9.21. So should we reject or not reject the null?
No.
Do not reject the null. This is the rejection region out here. So for step D, you'd say do not reject the null hypothesis. Do not reject the null. In other words, our observed values were close enough to our expected values that we cannot reject these percents. So our claim was down here, though. When the claim's down here, you use the word support. So if we're not rejecting the null, that means we think these percents are probably true. Okay, we don't know for sure, but the evidence doesn't say they're not true anyway. So that means we think the alternative is probably false. So we'd say there's not enough evidence to support the claim for step E. There's not enough evidence to support the claim that the percents are incorrect. You can just leave it on that. Look, put it in the red tray, please. Any questions about this?